Last time when we talked about solving exponential and logarithmic equations, we were able to come up with a new way of solving equations, particularly when you're unable to create the same base on both sides of the equation, and that involved taking the log of both sides and solving for x. So we are going to be working more with that today, particularly as it comes to applications. So let's take a look at example 1. The skeleton of a mastodon has lost 58% of its original carbon-14. Recall that the half-life of carbon is 5,730 years. When did the mastodon die? Now we need to remember which equation we want to use, what type of application this is. This is a radioactive decay problem. We have the half-life of carbon given to us. And so we should recall that this is the formula that we want to be working with. P is the amount that you start with, 0.5 to the x over h. So h is where you're going to put in the actual half-life. X is going to be the amount of time that has passed, and then f of x represents the amount that is remaining. So filling in what we know, it says that the skeleton has lost 58%. That means it still has 42% remaining. If it has 42% remaining, and we started with some amount p, then on the left-hand side we can write 0.42 p. Now we don't know what x is, that's what we're trying to solve for. When did the mastodon die? So how long ago did the mastodon die? And h is the half-life of carbon. Now that we have plugged in everything we do know, we can try to go ahead and start solving this. Now since we have a p on both sides of the equation, we can cancel that out. And so the only thing that we have left to solve for is x. Now since x is in the exponent, we are going to use our strategy of using the power law after we've taken the log of both sides. Now before, when we had talked about some applications, the way we went about solving these types of problems was we would graph the left-hand side and we would graph the right-hand side. We ended up with an exponential function and a horizontal line, and we would find the intersection of those two graphs. But now we don't have to do that. We can actually just go ahead and get right into solving. So I'm going to take the log of both sides. Again, it doesn't matter if you use ln, if you use common log, you could use log base anything. Usually log or ln are probably the easiest just because there are already buttons on the calculator for you to use. Okay, the next step is to use the power law and bring the exponent out in front. So the x over 5730, that entire exponent, that entire fraction comes out in front of ln of 0.5. And now we try to get x by itself. So we'll multiply both sides by 5730 and then divide both sides by ln of 0.5. That leaves us with x equals 5730 ln of 0.42 all over ln of 0.5. And then now we don't have to deal with any of the graphing. We don't need to find any intersection points. We just simply have to plug this in. So here's my calculator. I'm going to go ahead and plug in exactly what I just found x is equal to. And it looks like it's equal to 7,171.31.32 if we round that. Okay, so when did the mastodon die? About 7,171 years ago. Let's take a look at another example. A quantity of uranium decays to 2/3 of its original mass in 0.26 billion years. Find the half-life of uranium. Okay, so again, we're looking at half-life, so we're looking at radioactive decay, so we're using the same formula as we did in the last example. Now, it says it decays to 2/3. That means there is still 2/3 remaining, 2/3 of the original amount, P. Now, for this problem, though, you are not told what the half-life is, but you are told how much time has passed, 0.26 billion years. So in this problem, we are filling in the left-hand side, we're filling in for x, and we're going to have to solve for h. Okay, so 2/3 times p is equal to p times 0.5 raised to the 0.26 over h. We'll simplify this. Again, we have p on both sides, cancel that from both sides. And then we'll go ahead and take the ln of both sides. The h is still in the exponent, so we are still going to need to bring that exponent out in front, and the only way we can do that is by taking the log of both sides. The 0.26 over h now comes out in front, and now we have to solve for h. So for this, I would suggest multiplying both sides by h. So now h will be on the left, and then divide both sides by ln of 2/3 to get h by itself. That leaves us with 0.26 ln of 0.5 divided by ln of 2/3. Okay, now let's go ahead and use the calculator to figure out what exactly that is. So we have 0.26 ln of 0.5 in the numerator, and divide that by ln of 2/3. Now that comes out to be about 0.444. Don't forget that our value of h is going to be the same as the units of x. For this, x was in billion years, so our half-life will also be in billions of years. So the half-life of uranium is about 0.44 billion years. Let's look at a different type of problem. If $3,000 is to be invested at 8% per year, compounded quarterly, in how many years will the investment be worth $10,680? This is an interest type problem. Because it's compounded quarterly, we know that we want to use the compound interest formula. We know we're not using continuous compounding because it says that it's compounded quarterly, not continuously. So here's the formula that we had learned. And now let's fill in what we know. We're starting with $3,000 that's going to be invested at a rate of 0.08, right, 8%, so change that into a decimal. Compounded quarterly, so remember that n is the number of times that it's compounded in 1 year. So that's 4. In how many years will the investment be worth $10,680? That's your future amount, or A. We need to figure out what t is and how many years, right? How long will it take? So we're solving for t. Let's start by simplifying what's inside the parentheses as much as we can. So 0.08 divided by 4 is 0.02, and 1 plus 0.02 is 1.02. Next, I'm going to try to simplify it so that the portion that's being raised to the exponent is by itself. So notice that the 3,000 is not raised to the 4 times t. Only the 1.02 is raised to the 4 times t. So I want to isolate the part that's being raised to the exponent as much as I can before I take the log of both sides. In order to do that, I can divide both sides by 3,000, and that leaves me with 3.56 on the left, and then on the right, now I just have 1.02 to the 4t. Now we can take the log of both sides. We can move the exponent out in front, so we'll have 4t times ln of 1.02. And now we try to get t by itself. So it looks like we'll have to divide both sides by 4 and divide both sides by ln of 1.02. And then we're going to go ahead and plug this into the calculator. Now, it is important to note that for examples 1 and 2, there was no need for me to put the denominator in parentheses. Why? Because there was only one thing in the denominator. It was just ln of 2/3. In this problem, though, when you do put this into the calculator, you'll want to be very careful and make sure that the 4 ln 1.02 is all in parentheses. Otherwise, what the calculator can end up doing is dividing by 4 and then multiplying that answer by ln of 1.02. But you want to divide by both 4 and ln of 1.02. So let's put this in, and I'll make sure that we have the parentheses that we need. Notice there at the end that it looks like I put in 2 sets of parentheses. It's because one is for the ln portion, ln of 1.02. I closed that parentheses. And the other parentheses is to make sure that I close the parentheses for the entire denominator. So we get that our answer is about 16.03. So it's going to take about 16 years for the investment to be worth $10,680. Okay, let's take a look at the last problem. This one is a population growth type problem. So it says, a biologist knows that if there are no inhibiting or stimulating factors, the population of a certain type of bacteria will increase exponentially. The population at time t is given by the function s of t equals p times e to the rt, where p is the initial population and r is the continuous growth rate. The biologist has a culture that contains 1,000 bacteria, and 7 hours later, there are 5,000 bacteria. Part A. What is the growth rate of the bacteria? And then part B. When will the population reach 1 billion? Let's start with part A. What is the growth rate of the bacteria? Let's fill in what we know. Now, because in this example, you're given the actual function to use, s of t equals p times e to the rt, you actually know that this population is a continuous growth problem. The e in there indicates that. P is the initial population, r is the continuous growth rate. Now we know that there were 5,000 bacteria after 7 hours, and originally this contained 1,000 bacteria. So let's fill this in. So 5,000 is the amount of bacteria we had after 7 hours, and we started off with 1,000. So we need to figure out the growth rate, which is r. So it looks like that's the only thing that's left in there for us to solve. Again, you want to start off by isolating the part that's being raised to the exponent. So the 1,000 is not being raised to the 7r, so we need to isolate the e to the 7r by itself. So we're going to start by dividing both sides by 1,000. That leaves us with 5 equals e to the 7r. And now we need to solve for r. R is in the exponent, so we know we're going to have to take the log of both sides. Now in this particular case, it is helpful for us to use ln rather than common log. Why? Because eventually we'll have ln of e in there, and that will actually simplify our problem for us. So let's go ahead and bring the exponent out in front. Ln of 5 equals 7r ln of e. Ln of e we know is equal to 1, and that's where the simplification happens. Okay, we get r by itself, so this is ln of 5 divided by 7. Make sure when you put this into the calculator that you close the parentheses on ln of 5 before you divide by 7. And it looks like the rate is about 0.2299. So that is about 23%. Now that's part A. What's part B? When will the population reach 1 billion? Well, now that we know what the growth rate is, we can use that to figure out how long it's going to take to reach 1 billion. We'll use the same equation here, but we're filling in different things. We're still starting with 1,000 bacteria, and we want to know when it's going to reach 1 billion. Now, 1 billion, remember, is 9 zeros after a 1. And we found the growth rate. So I'm going to put in the growth rate with a couple more decimal places just to try to get us to be a little bit more accurate. So that's 0.2299t in the exponent. Now we're going to isolate the portion that is being raised to the exponent. So we are going to divide both sides by 1,000. That leaves us with 1 million on the left is equal to e to the 0.2299t. And now we take the log of both sides, bring the exponent out in front, so we have 0.2299t times ln of e. ln of e is equal to 1. And now we get t by itself. So divide both sides by 0.2299. And now we just have to plug this into our calculator. And again, make sure that you are closing the parentheses on what you're taking the ln of before you divide by 0.2299. And it looks like our answer comes out to be about 60. And now we just want to make sure that we're using the right units. So remember, the amount of time is in hours. So our answer is going to be about 60 hours.